Okay. Well, good morning, everyone, and welcome to the inaugural speaker for the HHP speaker series in artificial intelligence. I would like to thank Dean Reed for his support and enthusiasm for this speaker series. And we are very delighted to have with us today Dr. Bradley Baker. Dr. Baker is an assistant professor with the Mark McCormack Department of Sport Management, which is housed within the Eisenberg School of Management at the University of Massachusetts. Dr. Baker has a PhD in business administration and a master's in sports and recreation management, both from Temple, and his bachelor's degree is in computer science and mathematical science from Johns Hopkins University. He will be talking about that as well. Dr. Baker applies techniques from machine learning to problems in sport consumer behavior and sport analytics. And today his presentation will be about 40 minutes. He will talk to us about his journey with artificial intelligence and the connections to sport management. And after that, we'll have about 15 minutes for questions and open discussion with the attendees. Please put your question on the chat box so we can address the questions as they come in. And you can do that as you're listening to the presentation, but we obviously will not address them as they come in. We will just do it at the end of the presentation. And we'll work on these questions as time allows. So with that said, Dr. Baker, the Zoom floor is yours.
Great. Thanks, and thanks for those kind words of welcome. I'd also like to just start by thanking the College of Health and Human Performance for inviting me today. I'm excited to be here and to virtually see all of you and talk about some areas that I think are very interesting, and hopefully at least some of you will as well. Before I get started, just quick overview of the agenda, how I'm structuring the next 40 minutes or so. I'm going to start with a brief summary of my personal background, educational and professional, that I think helps provide some context for where I'm coming from in the statements that I'm making, what I'm talking about in terms of artificial intelligence. I'm going to follow that with a very high-level overview, think 30,000 foot overview of artificial intelligence, what it is, how it fits within other related areas such as machine learning, and trying to connect that specifically to topics within sport management and where AI either is being or could be applied into sport management topics, either in terms of academic topics or practitioner-oriented, the actual management of sport. And then I'll talk about a specific, very, very early stage project that I'm working on that I think will help make some of it a little bit more concrete and sort of show how this can be applied. I do want to caution this is an incredibly early stage project, so I won't be presenting results. I'll just be talking about sort of the setup of the study that I'm starting to work on. I'm currently in data collection on. And then we'll wrap up with a Q&A session, and we can talk either about AI and sport management, anything else that I presented, or general questions about sort of the future of AI in sport management and other related disciplines, anything that's connected to anywhere in the college. So that's where we're going to get started. Just again, my personal background. I did my undergraduate work at Johns Hopkins. I was a double major in computer science and mathematical sciences. Hopkins has since renamed that department Applied Mathematics. They have a math department as well. This is not that. This is a department in the College of Engineering that's very much on applied topics. So probability statistics, combinatorics, graph theory, that sort of thing. So as I mentioned, I had a double major in computer science and mathematical sciences. Was very much a computer science major who also did applied math. After graduating, I worked for a few years as a programmer, primarily working on developing language models based on massive text corpora, so collecting large quantities of text data and using it to try to understand how people use words in combinations how people structure sentences, uh, as a support role for a company that was working on trying to develop some speech recognition uh, techniques. During that time, I was also in the evening coaching fencing. I fenced competitively at Johns Hopkins all through college. I continued fencing at the national and international level, basically up until 2012, so not quite 15 years post college. But I started shortly after college coaching in the evenings and fell in love with coaching. That I enjoyed programming. My passion was coaching fencing, and decided that I wanted to make a career change into sport, and that was my future path was in coaching. And so, after about a year after I made that decision, had the opportunity to get a full-time job as the assistant coach with the women's fencing program at Temple University. It's a perennial top 10 NCAA program, where I was working with the epee and the saber fencers. For those of you who aren't familiar with fencing, has three weapons, what any other sport would call disciplines: foil, epee, and saber. Crossword aficionados, I'm sure, have seen epee because of all the E's. So again, I was working with the epee squad, with the saber squad, and I was the assistant coach at Temple for 9 years, during which I earned a master's degree in sport and recreation management, with the goal of that being something that was going to help my long-term plans as a coach. Uh, but towards the end of that program, was encouraged to continue studies in sport management by a couple of our faculty, and ultimately decided that was a really good fit for what I wanted to do. And so ended up stopping coaching and going into the PhD program in sport management, also at Temple. And so completed that in 2017. Took a slight hiatus at that point, where I had an opportunity to go co-found a startup company called D5AI, where we had some ideas of some novel approaches to something called deep learning, which I'll talk about probably in about 10 minutes or so. And so worked on trying to refine those ideas and get them to the point where they could be, in legalese terms, reduced to practice, submitted to the patent office, um, but always with the intention of that being a relatively short-term hiatus, with the intention of returning to academia. And so during that time, I was staying research active. I was continuing to publish in what I'll euphemistically call my free time, and had the opportunity a couple of years later to join the sport management department at the University of Massachusetts. So I'm currently in my second year as an assistant professor at UMass. Um, and I guess that's sort of the bit of a circuitous path of how I've gotten to where I am, and merging these two quasi-parallel paths between this computer science background and this sport management background. And that's sort of what informs a lot of the approaches that I take as I work in sport management now. My core research areas are sport consumer behavior. I focus largely on loyalty and brand building. And recently, a lot of this has been within the context of social media, of digital culture, of emerging technologies. As I do that, reflecting on my particular background, I'm actively looking for opportunities to apply techniques from machine learning to problems that otherwise would be completely mainstream within sport management. The questions that I'm looking at in terms of what gets a sport fan to stay loyal to their team, what gets somebody to engage with an athlete on social media. These aren't atypical questions in sport management. These are pretty much the heart of the play core sport management types of questions, but looking to perhaps apply different techniques, different tools to addressing these same questions. And sort of I see this as a way of leveraging what is a very atypical background in sport management, certainly as an academic discipline, that I have experiences and skill set that are, if not unique, at least distinct from what you would typically see, and hoping to use that to get a different angle on some of the questions that I'm looking at, even if the questions are something that are pretty mainstream in our discipline. And similarly, in terms of teaching, I teach our sports analytics track, so I teach at both the undergraduate and the graduate level at UMass. So again, that's a nice area that helps bring together these disparate parts of my background and my experience. So that gives you a sense of where I am, where I'm coming from, how I've sort of brought together where those experiences and that training, and why I can apply it into looking at that intersection of AI and sport management. The next portion of what I want to do is talk about AI, artificial intelligence. And I think the key thing when you want to talk about something is to start by figuring out, what is it? What's the definition of the term? So this isn't always a great way of defining technical terms, but just a couple definitions out of mainstream traditional dictionaries. In this case, you'll see that the definitions are highly comparable. They invert the order of whether they're talking about doing it or the field of study of artificial intelligence. But whether you're looking at the OED or Merriam-Webster, these are pretty consistent definitions. And I think the key part of this is the idea of taking machines and having them simulate or imitate intelligent behavior. And it is key that it's simulation. There are definitely people that are trying to model the process in the human brain and replicate that in a computer, in the silicon. But for the most part, the dominant model is, can you get the results? Can you get human level performance or superhuman level performance on tasks that we normally think of as requiring intelligence? And that is very widely defined, and it's sort of a running joke that in the AI community that what is AI? It's whatever we haven't yet trained a computer to do. Once a computer can do it, it becomes commodified, and that's not intelligent, because any computer can do it. And there is some truth to that joke, and part of why AI never really is achieving what its sort of goal is because it keeps moving the goalposts on itself. But the main idea is taking a machine, taking a computer, and having it do some task that we normally think of as indicative of intelligence. Another way to look at this is to break down what falls under artificial intelligence. And there's a couple ways of doing this. The first one is looking at what are the methods or the techniques. And this is a very broad view of artificial intelligence. There's a lot of different ways of training a machine to do what we would think of as an intelligence requiring task. So just a couple examples. Expert systems are an approach where you try to distill what is it that human experts do when they're making a decision. Can you convert that into a series of rules, whether this is if then else statements or otherwise very codified, what's the process that human experts use in making a decision? Evolutionary computing, this is a lot of things like genetic algorithms, so very obviously, as you can tell from the names, inspired by biology. And so creating different ways of approaching a problem and having multiple systems effectively compete, kill off the least good, mutate the next generation of the best solutions, and the idea being try to evolve a more intelligent system. And all the way over at the left, machine learning, which is incredibly broad, and virtually everything that's in a state-of-the-art system today would fall into this category. And so when you're talking about practitioners in AI, almost all of them would consider themselves to be doing machine learning. AI is almost a marketing term at this point. AI is artificial intelligence is broader than just machine learning. Machine learning is a subset of artificial intelligence. That said, it's the subset where virtually all of the activity is taking place. And I'll be breaking down the machine learning section of this in the next slide. There's another way to look at this. Instead of looking at the various techniques and the various methods, is to look at how do you apply this artificial intelligence, this computer-driven decision-making on tasks that we normally think of as requiring human intelligence. And so you can look at this as a categorization or a typology. And so common things that we're going to see here are predictive analytics, natural language processing, which, as I mentioned earlier, is where what I was working in the space I was working in when I first came out of school as an undergrad. And so this is looking at how people use words in combination. There's a lot of activity in computer vision. And so whether this is recognizing what an image is or tracking things within a moving image. And so this is an approach where you're looking in the application orientation versus the technique orientation. And any of these applications can be addressed with any of these methods. And so it's the combination that you'll see in any actual system that's working. I want to break down the machine learning a little bit because, again, this is where a lot of the activity is, but it can be further categorized or divided into a few key areas that have different techniques will work for each of these areas, and they're most applicable to different types of problems, different classes of problems. So the big three areas are reinforcement learning, supervised learning, and unsupervised learning. So reinforcement learning, the core idea is that you take a system that operates within an environment. This could be the real world. This could be a simulated environment on the machine, and it takes actions and it gets feedback based on those actions. If it does something that's good, it gets a reward. If it does something that's bad, it gets a punishment or a negative reward, depending on how you want to frame it. Those rewards can be either immediate after every step, or they can be deferred. It makes it much harder to train if it's a deferred reward. However, there's a lot of real world tasks where you don't have an immediate outcome. It's multiple steps before you understand, okay, as you know, take this from a human perspective. If you're looking at a hockey team entering the offensive zone and the passes that eventually result in a shot on goal, and maybe they score, maybe they don't, how you enter the zone matters. It affects how likely that team is to score the goal, but there's no immediate feedback on that. You don't know how good that zone entry was until maybe 35 seconds later you get a quality opportunity or you don't. And so understanding how to do that, that's sort of the core of reinforcement learning. This has been hugely successful in machine learning in certain domains, most notably in game playing. And so if you're looking at AlphaZero, the chess playing program, or what I think is the most outstanding result is AlphaGo, the Go playing system that beat Lee Sedol, perhaps one of the best human Go players of all time. Go's in some ways very, very simple game, but also has incredible branching of possibilities. And so any type of a deep search of the future just explodes exponentially. And so this was being able to be human level performance at Go was for a long time considered a holy grail of artificial intelligence, that this would be so difficult that by the time a computer could reasonably be human level, clearly huge progress had to be made. And this happened a few years ago. And AlphaGo is at this point better than any human has ever been, and in all likelihood ever will be. And so that was sort of a huge breakthrough in the AI space, in the reinforcement learning space. Where do we see that as being applicable outside of beating humans at board games? You could see this in sport, maybe in developing, trying to apply those same techniques to learning strategic or tactical decision making. So the example that I was talking about on how you do a zone entry and what you do in the the play in hockey. There may be some applications to this in looking at more the business side of sport, the management side, understanding what's likely to happen if you make certain managerial decisions. I think the translation from what's been done in reinforcement learning into sport is much closer when you're looking at the in-game tactical decision making. So that's where I would see this likely to be making some breakthroughs in the next few years and really informing practice. Supervised learning, this is where you have a lot of data and you know at least some of that data that you can use for training, you know what the answer is. And so this is typically either regression problems or classification problems. And so you have a whole bunch of independent variables and you have a dependent variable and you're trying to create the associations, do prediction of the dependent variable from the independent variables, or commonly classification examples. A lot of this classification is just binary classification, yes, no, true, false. So an example in sport would be a season ticket holder. Either are you going to have that season ticket holder renew, or is that season ticket holder going to churn? Well, that's a classification problem. Are they staying or are they going? And that's the type of problem that supervised learning techniques are very good at doing. And trying to say, okay, well, we have a lot of examples of season ticket holders in the past. We understand their characteristics and we could observe whether they renewed or churned. Can we use that to understand what it is that is associated with that outcome, with that decision, and therefore for someone where we haven't yet seen that decision happen, understand, is this person likely to renew or churn? Or how many of our current season ticket holder base are likely to renew or churn? Unsupervised learning is fundamentally different in that you don't have data where you know the outcome on. And so this is where you have data, you want to understand some structure under it, but there isn't anything already a priori known about the structure. You can't label any of the points. That said, you can convert from that situation to supervised learning by applying, say, human labeling, but that's incredibly resource intensive. People time is much more expensive than computer time. And so there's a lot of situations where you can get huge quantities of unlabeled data, and unsupervised learning techniques are designed to get value out of that situation. The most prominent of this is clustering. And so key thing that you would see here is something like customer segmentation. And so understanding that these 100 customers are in some way similar to each other. It's unsupervised, so you may not know what it is about them, but you know that they tend to behave like each other. And if somebody else ends up near them in whatever metric you're using to assign similarity, you can expect that their behavior is also likely to be similar to the people that you've already assigned to that cluster. It can be useful to then post hoc label those, but that's really a user convenience so you can talk about what this cluster means. The technique is just to identify data points that are similar to each other. Or dimensionality reduction, which is actually the area where the research project I'll be presenting towards the end falls into the dimensionality reduction under unsupervised learning. And I'll get to that basically when I get to the project I'm going to be talking about. And that'll hopefully make more sense. The other big question about AI, and I hear this a lot, is why now? Why is AI a hot area? Why does this speaker series exist? Why did you invite me to come join you for an hour today? Why do we see hiring where that's part of the criteria? We're looking to add it. We're looking to add it to our curriculum. It's why is this in the news? Why is this, why did, I think it was Fortune that declared data science to be the sexiest job or sexiest career of the 21st century. Like, what is it about AI? Why is this a hot topic right now, as opposed to 10 years ago, 20 years ago? Artificial intelligence has been around since the 1950s. This is not a brand new thing. It is absolutely a super hot area this decade. And so what is it that happened that caused that to occur? And it's really a combination of different factors that all contributed to this. The first is that there were a series of new algorithms that were very broadly applicable to a large range of tasks that were incredibly successful, that just took the state of the art on a lot of different tasks and jumped the level of performance. This was probably the most prominent of this was deep learning. So this is artificial neural networks that have more than just what's called one hidden layer. And so artificial neural networks that are getting up to 3 or more, and this extends to hundreds of layers. Artificial neural networks are a stylistic representation of how the human brain, or any animal brain, I guess, works, done in a computer. These have been around since the 1950s. Perceptrons and neural networks were one of the first approaches used in AI. They were good up to a certain point and then basically hit a ceiling and were never the state of the art after that until 2012. There were some techniques that were discovered or invented, however you want to think of that, that allowed training for deeper networks and efficient training for deeper networks. And once you got to that, suddenly the state of the art performance on a whole wide range of tasks took off, starting from computer vision, but then the same techniques being applied to all kinds of other classification and regression problems. The second factor that we're seeing is hugely enhanced availability of massive quantities of data. We talk about this all the time, big data, everything online, how much information is being created in the world. Machine learning algorithms tend to be incredibly data hungry. They need massive quantities of data to be able to do well. And more or less, the more data is available, the better the results are. And so as we've seen huge increases in the quantity of data, that's contributed to the success or the efficacy of the techniques that are very data reliant. And then finally, a third factor that happened more or less concurrently with these other two were some advances in available hardware. This is primarily in GPUs, graphics processing units, and TPUs, which are tensor processing units, that have become widely more available and have become incredibly more powerful. So in your computer, the chip that basically runs your computer, that does all the calculations, is the CPU. That's just sort of the heart of the brains of your computer. A GPU is a specialized type of chip that's very, very good at doing simple calculations very quickly. Where this is usually used for is on graphics, hence the G in the GPU. And there's basically 3 different communities that have really pushed the GPU development, and there are the sort of 3 distinct core markets of the GPU market. And probably the leader there, well, not probably, the leader there is NVIDIA, and everyone else is just trying to catch up as NVIDIA keeps jumping a generation ahead of everyone. But those 3 target markets for them: super high-end gamers, so people playing video games, lots of graphics in video games. Having a chip that can do that a little bit faster and a little bit better is hugely valuable if you want to reduce latency, if you want to reduce lag, and be able to do just a little bit better at CS:GO or whatever video games you're playing. AI developers, which is definitely smaller than gamers, and then finally Bitcoin miners and other cryptocurrency miners, which again is another application where you get huge quantities of very simple calculations. And that's what GPUs are designed for. These 3 markets, which are definitely distinct markets, drove a lot of very rapid advance in hardware. And AI is definitely getting to take advantage of the fact that there is this massive high-end gaming market that caused NVIDIA and their competitors to launch ever better chipsets. And then the AI community just sort of rides on the coattails of the gamers, which is, I think, interesting and a little bit odd, and not normally how we think of as massive advances in industries off of something like gaming. That said, there is definitely a ton of hype around AI, and this has been endemic to AI from the beginning, from the 1950s. Another running joke that has a little bit too much truth in the AI community is that the amazing breakthroughs are always, this is where we're going to be in 10 years. And that was true in the 1950s. That was true in the 1980s. That's true now, that we're always just almost on the cusp of solving the world. And so this is the Gartner hype cycle, which is not AI specific, but the idea that there'll be some new innovation. Everybody goes pouring in. They have these sky high expectations. Reality comes and hits, and just everyone gets disillusioned. You get this crushing depression in the expectations. And then finally, as people start to figure out how the innovation actually works, how it actually contributes, you get this slope of enlightenment and this plateau of productivity. Well, AI has gone through these cycles repeatedly, and into what's known as an AI winter, when suddenly all the funding dries up, all the people move out and they go on to other topics. And then something new comes along and we get this spike in expectations again. I mentioned starting in 2012 with deep learning, there were these breakthroughs. The expectations relative to 8 years ago are sky high. The AI communities like to, really seems to the consensus is, well, maybe this time is different. Maybe this time we really did get the breakthrough and these sky high expectations are real and we can level out from this level. Certainly past history has seen a huge drop off of the point about where we are now. That said, there's continually more breakthroughs not even every year, every month. There's tens of thousands of papers coming out in this space that keep pushing the envelope of the state of the art in area after area. So maybe it's right. Maybe they finally broke this cycle and the expectations are actually reasonable, even with how quickly they came up. Some use cases that we see in sport management, and I'm getting a little too excited about this, so I'm running a little bit a lot longer than I'd intended. So I'm going to start to try to move through this relatively quickly. But one of the things that we're seeing, or places that you could apply this, is looking at where are we getting data. We're getting huge amounts of data on customer behaviors or more generally consumer behaviors. There's all kinds of wearable sensors, whether this is something like a Fitbit on an individual consumer working personal informatics type, or whether this is, say, the RFID chips that are in the shoulder pads of every NFL player, or other wearables that you can put on athletes to track what their bodies are doing as they do their sport or as they do training. And things like in-stadium cameras, whether that's tracking the players and the flow of play, or whether you're using that to monitor your crowd and your spectators. There's huge amounts of data that are coming online now. And where you can see the AI applications are, how do you identify patterns in all of that data? How do you gain novel insight? With the goal being making better decisions faster. Either identifying things that there's just too much data for a human to really see that pattern, and so have the computer assist the pattern identification, or be able to do it with less human effort. Because again, human effort is frequently the limiting constraint. And so the more you can get the humans out of it, the more you can put the AI into a support role, the better the decisions will be made. And so this is, all kinds of things. If you're talking about sport performance, you can look at player evaluation, in-game decision making, injury prevention, training optimization, helping people go through the right lifting routine and understand what type of load to put on their body. You can see this in business applications, trying to predict consumer behaviors, trying to do some prescriptive analysis, not just here's what happened or here's what we think will happen, but here's what we should do to make better outcomes happen in terms of the business of sport. We see this a lot with automating media, and so creating automated highlights from a game, generating narrative stories just from the statistics. So this is great if you want to expand sport. There's lots of coverage at the major league levels, but how do you develop sport journalism at a level where it's too low to really assign a human reporter to? Can you automate that and have some value, even if not as good as having that human reporter covering, say, the Marlins? And then in terms of improved health outcomes, and so this is maybe more not the elite level sport, but the individual people that are doing health, that are doing fitness, that are doing recreational sport. How do we tailor exercise plans? How do we tailor interventions to help enhance health outcomes. And so these are all sort of the areas where using this massive new data and using these techniques coming over from machine learning, where you can see these being applied into sport management. There are a ton of challenges with this, figuring out how to integrate that into existing systems, the interpretability of these systems. An awful lot of the cutting edge ones are what's known as a black box. They give you an answer, but they give you very little information about why. So neural nets are horrible for this. They're incredibly complex. It's you get the answer, but no justification for why that's the answer is the answer. This is a leading edge area of research in the computer science field on trying to enhance the interpretability in a lot of the sort of common systems that are black box. Since I'm running short on time, I'm going to try to give a quick run through of the study that I mentioned that I was working on. And again, this is really early stage. So this is just setting it up and showing how I'm applying one of these techniques into a question that you would normally see in sport management. So this is a project that my working title is Birds of a Feather Using Word Embeddings to Evaluate Athlete Brand Similarity. So a bit of context for this that's not specific to the method. What I'm looking at is athletes as brands and how do you value them, whether this is as endorsers or otherwise, their value as a brand, as a brand entity. And so this is largely pulling out of human brand theory. So the precepts of human brand theory are that consumers form attachments to well-known personas, star athletes, that are attractive, and that those attachments then can be the basis for positive marketing results. That if I like LeBron James and LeBron James is partnered with Nike, you know what, maybe I should go buy some Nikes. And some of the key work in applying these ideas into sport management are actually coming out of your college, out of your department at UF, and so I cite some of your faculty basically on every paper that I write in this space. So it's kind of cool to be talking to some of you about this. But the core argument is that having a strong personal brand can be among athletes' most valuable assets. So to make this more concrete, Forbes declared or announced Roger Federer as the highest paid athlete of 2020. In the last year, he made $100 million from endorsements. And so this is certainly his partnership with Uniqlo, but also, Credit Suisse, Rolex, all, probably a dozen other partners. He made 6.5 million in winnings. He's one of the best tennis players of all time. I think he's currently ranked 4th in the world, top of his profession. And what he's making in endorsements is dwarfing what he can make actually doing his sport. And so that's all off of the fact that Federer has an incredibly marketable brand. It's very positive for companies to be able to associate themselves both with his success, but also all of the rest of the associations, very clean cut, very, very, the type of positive associations you would want to have with your brand. Now, sport management has looked at this in a lot of different ways. We have a bunch of existing scales to measure and assess things like athlete brand image or the brand associations that we have either on an individual athlete level or on a team level. These are all great. These are, this is good literature. These are scales that I would use, that I cite. But the core idea of the study that I'm talking about now is to take a novel approach to this. Let's take a different perspective on it and see if we get sort of more nuanced understanding of it, or what do we see from taking just a different approach than the types of scales that we already see that are established in the sport management literature. So the idea here is to borrow some techniques out of the natural language processing realm, specifically something called word embeddings. And the idea here is to create a latent semantic representation of words, so understand the meaning of words based on the words that occur around them. And so in this case, what I'm applying this to is the athlete brands. And so understanding what are the latent representation, what's the mental representation of an athlete brand in consumers' minds based on the words that consumers write about them. So the idea here is to take a huge quantity of text and reduce this down into something called a vectorized representation or a vector representation, basically a smaller number of numbers that can represent that collective, that meaning of the word, or in this case, the words that I'm going to be looking for the meaning of are the athlete brands. And so this is driven out of some work that was done out of Google starting in 2013. They launched a technique called word2vec. There have been several other approaches to word embeddings that don't follow the Google approach since then, but that all more or less serve a similar purpose. And so the idea is to be able to take representations of every word within a vocabulary. And so you might have 50,000 different words. In computer science, they do something called one-hot encoding. This is what probably for all of you, you're more familiar with hearing this as dummy coding. The idea being you're representing a particular word with a whole bunch of zeros, a whole bunch of variables that it isn't, and one variable that it is. Take those, apply as the input into a very small neural network. You have a single hidden layer, and then you have an output layer. The hidden layer is much lower dimensionality than the input layer and the output layer. Each of those have dimensionality of however many words are in your vocabulary. The hidden layer might be 100 dimensions, it might be 200 dimensions, so the number of nodes. And the idea is, how can you map from what you start with, this very sparse representation, this one-hot or dummy coding representation of the word, to the context that the word appears in through this highly constrained middle layer, where you only have 100 nodes or 200 nodes. And the idea is to figure out what are the weights on these connections from each of these layers. The weights going from that input layer to that hidden layer are the vector that we're talking about with these words. And so if you have 100 nodes in your hidden layer, you have a 100 by 1 dimensional vector that represents what do we understand in this constrained middle layer about this word. And that's effectively the semantic meaning of the word. Words that are similar, words that are associated with other words in their context, will end up with very similar patterns in their weights going into this hidden layer. And that's the key takeaway. And that's where these vectors, the more similar they are, the more similar the starting words are. And so what can we do with that? We can start to understand what these meanings are. We can start to understand what the latent representation, the understanding the representation that perhaps a consumer can't tell you exactly this is what I'm thinking about, but based on the words around it, I'm using this brand in the same way that I talk about this other brand, or in a very different way than I talk about this other brand. And so looking at the words around the brand when somebody's talking about the brand can help therefore provide insight into what do we think of when we think of the brand. The data I'm going to be using on this is going to be Twitter data. So looking at tweets that mention an athlete, I'm going to be using athletes, both the NBA and the WNBA, including athletes that aren't yet in the league. So NBA draft is coming up in a couple of weeks, grabbing the representation of these athletes before they're actually in the league, before they're actually associated with the teams and have done anything in the NBA, and trying to understand how do these different athletes, how are they viewed by consumers? Ways that I expect to be able to use these vector representations from this word embedding, identifying athletes who are similar. So athletes that are talked about in the same way. So this has some practical uses. Let's say you're a firm that's looking for an endorser. You have someone you're like, you know what, that person really resonates with our customers, our potential customers. Unfortunately, they've already signed an exclusivity arrangement with our competitor. We can't sign them as our endorser. Who else do consumers think of in the same way? Maybe that's going to be a good endorser for us. And so looking for that substitutability of endorsers. These word embeddings, because they're vectors, there's all kinds of, I'm going to try not to get too deep into the details here. There's all kinds of algebraic transformations where you can basically add and subtract these vectors to look at representations. If you take a LeBron James and subtract out him being on the Lakers and instead put him on another team, who would that be like? And these vectors, actually, the way that they work, you can do that type of algebraic transformation and get meaningful results. You can also get complex semantic relationships from these vectors. And so throw back to SATs back before they took analogies off of them. If you think of, Aja Wilson is to the WNBA as who is to the NBA. In other words, who's the Aja Wilson of the NBA? And so looking at that type of understanding of what's going on in terms of these brands. There are some limitations to this. How the text around how people talk about brands may not fully encapsulate how they think of the brands. And human-generated text is prone to social biases. And so a lot of these word embedding techniques, it's been repeatedly identified, they capture the type of biases that we see, certainly in terms of gender stereotypes, in terms of racial stereotypes. And so understanding how that impacts the conclusions you can draw from the types of comparisons that you would be making with these vector representations from these word embeddings. But what I'm looking for here is just better understanding of how we think about brands, better understanding of what are the associations, whether it's specific brands or generally across these two leagues, and establishing a foundation to go look at more in terms of the value of endorsers or what influence endorsers have. A couple key takeaways before I kick us over into the open Q&A and hopefully address some of your questions. Artificial intelligence is a tool. It is not a silver bullet. I get conversation that I have more frequently than I would like. I can kind of paraphrase as someone coming to me and saying, hey, we have a whole bunch of data. Can't you just do some of that machine learning stuff and get us some results? It absolutely does not work that way. You don't just pour data into a pile and stir it up and results pop out. That said, these techniques have been getting some amazing results. There are some things that if you had asked me 10 years ago, I said, there's just no way 30 years out that we're going to see that. And 5 years later, it was there in production. That said, they're also associated with some even bigger claims of that, that hype cycle in that Gartner hype cycle of, really that super high expectations that, artificial general intelligence being being able to do anything a human can do is around the board. We're not there yet. So there is even more, as amazing as the results are, the claims are even bigger. A lot of this is driven by the amount of data and the amount of computational resources that are available. That said, it's impossible to compete with a Google, with a Microsoft, with a Baidu, if what you're doing is, let's see who has more data, who has more computation. There's about 6 firms in the world that are in that tier that are just going to win that competition every time. But that said, both the amount of data and the computational resources are just getting incredibly more accessible, incredibly more cheap, that you can actually use this, whether as an individual researcher or if you're, say, a team and you're looking to apply some of these techniques into what you're trying to do in your business. What do we need to do this? We need a lot more work on developing tech tools, developing methods, making them much more accessible, making it where you don't have to hire a whole team of data scientists to be able to do a basic system. And there's huge progress coming here. This is where we need more progress. We also, we're all in academia, huge demand to educate our students to be able to operate in this world, to be able to take advantage of all of these new tools, all of these new techniques. And that's really not clear sort of a path forward there. We absolutely have to take a multidisciplinary approach. We need to coordinate between sport management, exercise science, biomechanists, data scientists, statisticians, get all of these people into the conversation, get everybody working together in order for this really to come to fruition. So sorry that was a bit rushed at the end. Looks like we have about 10 minutes for question and answer. So I'm going to try to address some of that in the time.
Thank you, Bradley. Do you mind stop sharing your
yes.
That'd be great. Thank you for a great presentation. So my end clapping. Thank you so much. I'm going to stop the recording now so we can have our Q&A session. So here it goes.
Okay, so